Wasza Ekscelencjo, Szanowni Państwo, witam Państwa bardzo serdecznie na kolejnym wykładzie z serii Zapytaj Fizyka. Dzisiejsze spotkanie jest organizowane przy współpracy Ambasady Francuskiej, Instytutu Francuskiego w Polsce i gościmy znakomitych gości. Pozwólcie Państwo, że spróbuję w języku naszych gości przywitać. Son Excellence, Monsieur Président, Monsieur Ambassadeur, chers collègues, chers amis, bienvenue à la Faculté de physique de l'Université de Varsovie. Cette soirée est organisée en collaboration avec l'ambassade de France et l'Institut français de Pologne. Je suis très heureux et je suis très honoré d'accueillir au nom de la faculté Son Excellence, Monsieur Frédéric Billet, ambassadeur de la République française en Pologne. Je salue également mon collègue et ami, le professeur Zygmunt Lalak, vice-recteur de l'Université de Varsovie. Je salue cordialement Madame Francoise Combes. Madame Francoise Combes est la professeure titulaire de la chaire Galaxie et Cosmologie au Collège de France. Elle est honorée par de nombreuses distinctions internationales. Professeur Combes va présenter une conférence intitulée Histoire de l'univers. Moi, je m'appelle Darek Wazik, je suis doyen de la faculté de physique. Et moi, je vous souhaite à tous une excellente soirée. Et maintenant, je donne la parole au monsieur l'ambassadeur. S'il vous plaît.
Dobry wieczór wszystkim, panie rektorze, panie dekan, madame le professeur, szanowni państwo. Mam wielką przyjemność otworzyć dzisiaj wieczorem ta konferencja z dwóch powodów. Po pierwsze, to dla mnie niesłychany przywilej wygłosić przemówienie tutaj, w tym prestiżowym miejscu, a po drugie, ponieważ od dawna interesuję się astrofizyką, która, jak wiadomo, pozwala nam i pomoże nam dowiedzieć się więcej o kosmosie i o nas samych. Przy tej okazji chciałbym serdecznie podziękować organizatorom tej konferencji i pani Francoise Combes za jej udział. Przyjechała specjalnie z Paryża, aby podzielić się z nami swoją wiedzą, swoimi doświadczeniami, a również jej wątpliwościami na tematy, które są bardzo kompleksowe, skomplikowane albo pasjonujące. Pani profesor Combes jest astrofizyczką, profesorem katedry galaktyki i kosmologii w Collège de France w Paryżu oraz członkinią Francuskiej Akademii Nauk. I chciałbym przypomnieć, że 2 lata temu uhonorowaniem jej kariery było wręczenie złotego medalu Francuskiego Narodowego Centrum Badań Naukowych, to oznaczenie jest najwyższe odznaczenie naukowe we Francji. Astrofizyka, jak już powiedziałem, to jest bardzo merytoryczna i przydatna nauka, która pozwala nam lepiej zrozumieć, skąd podchodzi wszechświat. Ale cały czas udziela nam astrofizyka permanentnej lekcji pokory i tego z wielu powodów. Po pierwsze, wiadomo, a to są naukowcy nam mówią, że posiadamy wiedzę zaledwie na temat 5% materii w wszechświecie. Wiemy również, że bardzo mało na temat ciemnej materii i ciemnej energii, i o ciemnej energii, o której wiemy tylko tyle, że od kilku lat przyspiesza ona ekspansję wszechświata. Wiemy, że na przykład te galaktyki oddalają się od siebie, a tak zwana stala Hubble pozwala nam oszacować prędkość ich ekspansji, ale jestem pewien, że pani dzisiaj wieczorem, pani profesor, powie nam sporo rzeczy na ten temat. I po drugie, ponieważ naukowcy starają się zrozumieć, w jaki sposób na początku swego istnienia niezorganizowany wszechświat przekształcił się w ustrukturyzowany kosmos dookoła gwiazd, galaktyk i czarnych dziur. To jest bardzo, bardzo ciekawa dziedzina nauka, ale to dostrzeganie jest często ekscytujące i gdy przewijamy film z historii kosmosu wstecz, uświadomisz sobie, że wszechświat istniał przez większość czasu bez ludzi. To są to bardzo, bardzo ciekawe tematy i tak, można powiedzieć, że naukowcy pukają do drzwi nieznanego, a nikt jeszcze nie potrafi otworzyć te drzwi, a nasza niecierpliwość bardzo często wzmacnia tylko naszą wolę poznania. To powiedziawszy, chciałbym jeszcze podkreślić, że dzisiejszy wykład pani profesor Combes pozwoli wszystkim zagłębić się w te tematy, które dotyczące czasu i przestrzeni, oraz spróbować pojąć tajemnicę tego ukrytego wszechświata. Wiemy również oprócz tego, że kolejne lata mogą być determinujące dzięki użyciu nowych instrumentów, jak na przykład europejskiego satelity Euclid, którego wystrzelanie planowane jest w przyszłym roku, albo obserwatorium imienia Vera Rubin, które na przykład pozwoli nam obserwację supernowych, albo nie zapominając jeszcze o pierwszych zdjęciach latem tego roku teleskopu James Webb, które pozwolą nam również widzieć w ultrafiolecie na większą odległość i zbliżyć się do wielkiego wybuchu, czyli do początków wszechświata. To są, jak już powiedziałem, bardzo, bardzo pasjonujące tematy i można powiedzieć, że poznanie kosmosu pozostaje wielkim wyzwaniem dla nas, dla naszej potrzeby wiedzy, a też dla naszej ciekawości, ponieważ nurtuje ono naukowców oraz specjalistów, studentów od stuleci i można powiedzieć, że prawdopodobnie pozostanie kamieniem węgielnym wszelkiej myśli astrofizycznej w kolejnych latach. I tak, można na końcu, ja chciałbym przypomnieć, że Marie Curie-Skłodowska mówiła tak, jestem jedną z tych osób, która uważa, że nauka kryje w sobie wielkie piękno. Naukowiec w swym laboratorium jest nie tylko technikiem, jest także dzieckiem stojącym twarzą w twarz z zjawiskami natury, które budzą jego zachwyt niczym bajka. Niech ta refleksja Państwa inspiruje i pomaga Państwu w badaniach. Życzę Państwu owocnych debatów i dziękuję za uwagę.
Proszę Państwa, zajmę Państwu tylko minutę, ale nie mogę pozostawić ciepłych słów Pana ambasadora bez odpowiedzi ze strony władz Uniwersytetu Warszawskiego. Jestem bardzo wdzięczny Panu ambasadorowi, jestem bardzo wdzięczny Pani profesor Combes za to, że są tutaj dzisiaj z nami, że podzielą się z nami swoimi refleksjami, tak jak Pan ambasador, i swoją głęboką wiedzą na temat wczesnego wszechświata, co za chwilę uczyni Pani profesor Combes. Obecność tych znakomitych postaci jest najlepszym świadectwem głębokich, trwałych więzi, przyjaźni między Uniwersytetem Warszawskim a francuskimi instytucjami naukowymi. Panu ambasadorowi dziękuję, na jego ręce składam podziękowania za wieloletnią znakomitą współpracę między Uniwersytetem Warszawskim a ambasadą francuską, która zawsze wspierała nas w różnych chwilach, dobrych i złych, w lepszych czasach, w słabszych momentach. Mam nadzieję, że ta owocna współpraca będzie dalej układać się po naszej myśli, że dzisiejsze spotkanie jest jednym z licznych wydarzeń, które będą będą kamieniami milowymi tej współpracy. Dziękuję Panie ambasadorze, z góry dziękuję Pani profesor za ten wykład i przekazuję mikrofon gospodarzowi. Dziękuję.
Bardzo dziękuję. Jeszcze raz bardzo dziękujemy za ciepłe, miłe słowa. I teraz przejdziemy do już części naukowej. Et maintenant, je donne la parole au vice-doyen de la faculté, professeur Krzysztof Turzyński, qui va présenter la professeure Francoise Combes et présider la sortie scientifique de la soirée. S'il vous plaît.
Thank you very much. Let me say a few first words in the working language of tonight's meeting. I'm Krzysztof Turzyński. I'm a deputy dean of the Faculty of Physics, and I'm substituting here today Professor Piotr Sułkowski, who's running this series Ask a Physicist. This is our, the Faculty of Physics outreach effort that's concentrated on two things. First, we answer questions which are submitted to us via internet, and sometimes we try to answer the questions that haven't been asked, and these are the evening lectures of renowned specialists. So tonight, as we heard, both in Polish and in French, I'm going to say it again in English, we have a great pleasure to have with us Professor Francoise Combes, professor at Collège de France, the chair of the Galaxies and Cosmology, and a member of the Academy of Sciences. Professor Combes works at the Paris Observatory on the formation and evolution of galaxies, the dynamics of those galaxies, and their co-evolution with supermassive black holes. Models of dark matter is also something that she is a renowned specialist of. Professor Combes received many awards. Most lately, L'Oréal UNESCO International Prize for Women in Science, and also this was in 2021. 1 year earlier, she received the CNRS Gold Medal. Several years earlier, the Lisa Meitner Prize. This is a Swedish prize, and she's also a recipient of the Tycho Brahe Prize from the European Astronomical Society. Professor Combes was elected a member of the European Academy, and she served as the president of the French Astronomical Society. I really believe that there are few persons in the world equally qualified to tell us about the history of the universe. The floor is yours.
Well, thank you very much for this beautiful introduction and very kind introduction. So I'm very happy to be there and to speak today about the history of the universe. So history of the universe means not only the history from the Big Bang to the galaxies, stars and planets that we know now, but also how the astronomers in science, the history of science, in fact, how astronomers came up to know about the Big Bang and about our universe. So what you see here if I find the, yes. Here you see this Flammarion very well-known image, where it's just to illustrate that the human beings were always fascinated by the celestial sphere here, and they were curious to know what is behind, and we are trying to understand that. Well, to come from the beginning, much before the 20th century, there we know that people did not know a lot about the universe. We have some witness here, discovered recently in Germany, about the disk of Nebra. The disk of Nebra dates back to 1600 before Christ. So it's one of the oldest witness that people were looking at the sky. You see the sun, you see the moon, you see a boat even. And there are some association of stars that people have interpreted as the Pleiades, in fact. So we know that man, even at this epoch, look at the sky. Of course, they didn't know the shape, even the shape of the Earth. And the shape of the Earth was thought to be flat, as you see here. And it's very interesting that in different mythologies, China, Hindus, and so on, there was a lot of animals invoked here to support the flat Earth. And of course, here you have a tortoise, a giant tortoise, maybe because the back is round, I don't know. You have the sun here, the moon. And of course, there's a problem with flat Earth that when you have ocean and seas, you don't know where the water falls, in fact, as you see. So I will make a jump here directly with the Copernic Revolution that you all know here. And of course, you know that before him, we had the impression that we are at the center of the universe, we are the sun, and all the Earth was at the center, and all the other things, suns, the planets, and so on, were rotating around the Earth. And he had the idea to have a much more simple view of the nearby universe, that is a solar system at this epoch. And before there was Ptolemy, very complex orbits with epicycles and so on. It was very simple. You have the sun and the center fixed, and then all the planets were rotating in circular or almost circular elliptical orbits like Kepler showed. So this was called the Copernic Revolution in the 16th century. And of course, now we have taken lessons about that. We know that we are not at the center of the universe, that we have always the impression to be, and we call it the Copernican principle. And many in the history, this Copernican principle was invoked because, as you will see, yes. Now I jump to the 18th century, where Charles Messier was an observer in Paris Observatory, and at this epoch, people had discovered comets. And there was a Halley comet, and Halley gained a lot of glory because he was able to predict that this comet was coming back 70 years after. This was a very acclaimed discovery, and of course Charles Messier wanted to discover some comets also and have some glory. And so he made a catalog of objects. You see some examples here. So I don't know if we can have the light maybe less strong in the middle because we will see better the images. I don't know if it is possible. But anyway, here you see there is a lot of, thank you. Thank you, it's much better. Here you see that there are very different objects. Some are clouds in the Milky Way, clouds that are illuminated by stars. And you have groups of stars like the Pleiades. You have globular clusters, which are groups of 10 to the 5th 100,000 stars, very dense. And you have also galaxies. And here you have a galaxy and so on, Andromeda galaxy. Here you have a planetary nebula. Now we have a better image of these objects. And we know, for instance, Messier 1, the first, is the Crab Nebula. The Crab Nebula is a gas that has been expelled at the end of the life of this star that exploded in supernovae, and the Chinese people have seen it in 1,000 years. And you see a lot of clouds with different colors because they have different lines. Here you have a planetary nebula, and of course it's an error, this name, because people thought at the beginning that planets were born there, but it's not at all. It's the envelope of a star like our sun. At the end of our sun, we'll have a planetary nebula like that when all the gas around will be expelled. So we kept this name, but it is not a good name. And we have galaxy like Messier 51 that maybe you all know, interacting with another one. And of course, all these galaxies were called nebulae again, because they were diffuse objects looking like clouds, nebulae. And they are not nebulae. And there was also this kind of clouds, which is a dark clouds, absorbing the light of the stars behind. And now, if we jump again at the beginning of 20th century, now we did not know before 1930 that galaxies exist. It's less than 1 century that we know galaxies exist, which is surprising. Now we think that galaxies were known for a long time. No, there was a big debate in 1920, and these were the first leader of this camp here. Shapley was telling, well, maybe there is only one big entity, which is a Milky Way, and in fact it's our own galaxy, and all the objects that we see are included in the Milky Way. And Curtis said, no, there are different worlds. And this was also a philosophical idea by Kant, 18th century, that there must be other worlds than our own, and indeed, this was that. So why they were so ignorant? Why they were so ignorant? Because they did not know the distance of objects. All the objects are superposed on the sky, and we don't know how to measure their distance. Well, first, what we know in 1920, there was Vesto Slipher that were obtaining spectra in the Palomar telescopes here, and by the line of hydrogen and other elements, and by the lines they have the Doppler effect. You know, in the sound that there's Doppler effect when an object is coming towards you or receding. Here it's the same with light. So when the object is getting away from you, you have a red shift, and when it is coming towards you, you have a blue shift. So here Slipher measured a redshift of 1,000, 2,000 kilometers per second. So all these nebulae, that didn't know what were galaxies, these nebulae were going apart from us at 2,000 kilometers per second. It's huge, and they did not understand why. And the cartography, the mapping of our own galaxy was done by Captain. What he did, he thought that we were at the center of our galaxy. Again, we are at the center of the universe. He has not obeyed to the Copernican principle. And why? Because he did not know the distance of the various stars. And he said, well, maybe the stars are all in first approximation of the same luminosity. And if they are fading, that means that they are far away. And of course, he ignored the obscuration of the dust. When you look at the Milky Way, you see only the very local neighborhood, and all the rest is obscured by dust. Dust is obscuring the light of the remote stars. So it's like when you have a flashlight in the night. Of course, you are at the center of the light region, and here we are at the center because we see only the bright stars again. But of course, it didn't work. When you make a spiral structure of our own galaxy, the sun was in the center, and then the spiral was not at the center. So this was the main progress in this region was due to Henrietta Leavitt. Henrietta Leavitt was an astronomer in the United States, and her work was very tedious. She observed every night these stars and discovered variable stars, and she discovered 2,000 variable stars, and she was very patient and noticed that there is a proportionality factor between the intrinsic luminosity of the star, that they call Cepheids, and their period. Because here you see the star is oscillating like this, is going up and down, inflating, and when they are big, they are very bright, and then again, and there you have a periodic oscillation like this. And since you can directly make a relation between the period and the luminosity, then you have an indicator of distance. We call that standard candle. Standard candle, and this is why you have conclude the debate between Shapley and Curtis. And both Shapley and Curtis had something right. In fact, there was something right and something wrong. For instance, Shapley, which was wrong because everything was in the Milky Way, he knew that the sun was not at the center of the galaxy. Why? Because you have all these globular clusters in red here, and he knew that finally these globular clusters are all centered on the galactic center, of course, but they are not on the sun. So for this he was right. But of course he did not believe that there were other galaxies. Oops. Okay, so to end the debate, it was in 1925, 1926 that Edwin Hubble, that you see here, observed also in California, in Mont Palomar and Mount Wilson, and he discovered some Cepheids, so indicator of distance, in Andromeda. Andromeda is Messier 31, one of the catalog of Messier, and its companion, Messier 33. So he discovered that, and he could say that they are at 2 million light years from Earth. They cannot be in the Milky Way. So they are really external galaxies. So this is ending the debate. Now you know that there are a lot of galaxies, or a lot of other worlds. And also he discovered, after several years, when you have enough statistics, that there is a proportionality between the velocity, apparent velocity of the galaxy receding from Earth, and the distance, because you have the distance from Cepheids and the velocity. So this is called a Hubble law, but now also Lemaitre law, because he did not give any interpretation of this. For him, there was a Doppler effect of the velocities of the galaxies. They were really going apart from us, and in fact it is not. And even the priest, Belgian priest Georges Lemaitre, had the idea what was really the interpretation, and the interpretation that we have today is this one, that the universe is in expansion. Of course, to give you an idea of this expansion, we just reproduce the universe in 2 dimensions. It is the surface of the balloon. Okay, so you imagine that our universe is in 2D, and all the galaxies are on the surface of the balloon, and you inflate the balloon. So, of course, the galaxies don't move at all, but since there is inflation of space, they have the impression that all the galaxies around are getting out with a velocity proportional to the distance, but there is no velocity, as you can see. And, of course, the redshift and the blue shift that we have is only due to the inflation of space. Why? Because the photons that I have reproduced, like a sinusoid with a wavelength here, if you have a blue photons, then the photons, of course, is inflated with the universe at the same rate. So after a while, after the expansion in the universe, the wavelength is larger, and it is red and not blue, okay, because the wavelength is large. So the redshift is not a Doppler effect, it is inflation of the universe. And that's why you can have a redshift of a factor 10, which will mean that the galaxies are going much more faster than the velocity of light, but it is not, of course. The Doppler effect is just an apparent thing, but it works for only nearby galaxies. When you have very remote galaxies, it doesn't work. But it is only that. And this was understood by Georges Lemaitre. Why? Because Georges Lemaitre was a theoretician, and he knew about Einstein result. Just at about the same period, in 1915, Einstein devised that gravity is not a force like the other forces, like electromagnetic force, but it is a deformation of space. So again, to the clarity of the concept, our space is at 2 dimensions here. It's like a carpet. You have seen this kind of representation. And every star, like the blue thing is a star, our sun, for instance, and every star is deforming the carpet. And of course, all the other bodies are attracted to this because you have a potential well. Okay, and this is the relativity, and the equation of Einstein just relate the geometry of the universe to the content of the universe. So in one side of the equation you have the geometry, the curvature and so on, the curvature of the carpet, and in the second hand of the equation you have the quantity of matter and energy, and the more matter you have, the more curved will be the space. And of course in 1917 Einstein said, well, I can apply this equation to the universe, but it was he was very perplexed because the solution of the equation was either the universe is expanding or it's contracting, but there is no static universe. So what he did is, I know that the universe is stable, is constant, immovable, and so on. So I introduced this constant that he didn't find very beautiful, it's very ugly, but we need this constant lambda, cosmological constant it is called, and to make the static universe. But, of course, in 1929, Hubble finally, with this law, discovered, and Lemaitre discovered that, in fact, there is... Georges Lemaitre was making his PhD. He was an astronomer also, a priest, but astronomer. Make a PhD and make a paper in 1927, but in French. And no American reads French, so it was ignored. And he went then to California and talked to Hubble. It was like a postdoc in Caltech. And he knew about the paper of 29 2 years before, because he had discussed with Hubble. And then he made this first discovery, interpretation by linking the Einstein equation and the discovery of Hubble. And of course, at this time, he said, well, all the universe around us, if I look back in the past, it will be concentrated in one point. And it is the primitive atoms, he called. And of course, the Big Bang was called by Fred Hoyle much later in 1949. And Fred Hoyle did not like at all this theory of Big Bang. So he said to laugh at this theory, this is a Big Bang. But finally, the world stays until today. Now I jump again to another serendipitous discovery, which was confirming the Big Bang. It is a cosmic microwave background that I call CMB. And this was a discovery of Arno Penzias and Robert Wilson here. These two researchers were working for Bell Laboratories near New York. This is a telephone company, and what they wanted to know, if it was possible in the millimeter wavelengths, while the microwave is like in your oven, microwave oven, the wavelength is 2 millimeter. Okay? So they wanted to know if we can have satellites and you have communication, telecommunication in 2 millimeter wavelengths. And they were very surprised when their instrument is the big antenna that you see here, like a cone. And they were surprised to see a big noise. And this noise was not coming from the sun. They were not coming from the Milky Way even. They were everywhere constant, a constant noise. They say, well, maybe our antenna is not clean enough. They have cleaned a lot of... But it was there. And finally, they discovered this cosmic microwave background. You see, as a function of the frequency here, you have the intensity. So not only the number of photons, but multiplied by the energy of the photons, because they are very low energy. But even then, it's more energy in the cosmic microwave background than in all the optical background that we call cosmic optical background, and the infrared background, cosmic infrared background. All these background in blue and red come from all the stars and galaxies of the universe. So you say, well, it's a lot of light, but it's negligible by a factor 100 respect to the CMB. So it's really dominating a lot. And you have in this room, per cubic centimeter, 400 photons of the Big Bang. And since they are going at the velocity of light, you have 10,000 billions of these photons of the Big Bang crossing you by square centimeter and by second. So you are really heated by this microwave oven, if you want, coming from the Big Bang. But of course, if you put a television set without emission, you will detect this. Now, what we are seeing when you try to see the sky at 2 millimeter wavelength, what you see is a last scattering surface. And to illustrate this concept, you can go to the sun. What you are seeing in the sun is the last scattering surface. The sun is only gas. and the gas is ionized in the center, so it's protons and electrons. It's like the beginning of the universe. You have a lot, billions of scattering. So even if the light is coming with the velocity of light, it should take a few seconds to cross the sun, but it takes years and years and millions of years because it is scattered by billions times, okay? And it's only when it's optically thin, it's not scattered in a time, that the photons is transparent and is going in a straight line to the Earth. But here we call the surface of the sun the last scattering surface. Of course, you have still some gas outside the surface, but it is the surface where it becomes optically thin. And for the universe, it's the same. We have at the beginning a very dense and hot universe, plasma, electron and protons, scattering all the light. After the expansion of the universe, you reach at about 400,000 years, which is very small, with respect to the age of the universe, which is almost 14 billions. So very small after the Big Bang. You have the 3000 Kelvin. At 3000 Kelvin of the temperature, all the protons and electrons recombine in an atom, neutral. And then they don't scatter anymore the light, so you have the last scattering surface. And this is exactly what you see when there has been a lot of satellites at 2 millimeter wavelength. The first was Combes in 1992. There was then the WMAP in 2003 and Planck. The two first were sent by NASA, and the third was sent by the European Space Agency in 2013. And you see a part of the sky map here. You see that the resolution is much better now with Planck than with Combes at the beginning. But anyhow, what we discovered here is that, of course, there is a constant level of the mist because, as you know, the background is dominating all backgrounds. Then you subtract this constant, and what you find is this dipole. What is interpretation of this dipole is because our galaxy is moving with high velocity, 600 kilometers per second, with respect to the reference frame of the universe, which is the cosmic background. Okay, so we are moving at 6 kilometers, and we see more photons when in the direction of movement than the rest, so it's redder and blue. So you can subtract this dipole, and what you begin to see is the Milky Way. Milky Way is in the latitude 0 here, it's a coordinate of the Milky Way, and of course it's a foreground emission that you don't want. It's just a perturbing emission, so you subtract it because it's not a black body as the cosmic background. And then when you subtract the Milky Way, you find this. And this is fluctuations that you find in the cosmic background at the last scattering surface. They are real fluctuations. They are not noise at all. They are at the level of 10 to the minus 5 with respect to the background. So very small. You must have a large precision to see them. But they are the initial conditions of the structure of the universe. All these fluctuations by gravity will become structure like galaxies, clusters, and so on. And in between, the blue, which is less dense, by epsilon at the beginning, it will become voids, and the voids will become more voids, and by gravity, you will form galaxies. Now, we know also from Einstein equations what is the fate of the universe. Here you have in the ordinate the size of the characteristic size of the universe, which is expanding, and as a function of time in billion years. So we are here, and there are several possibilities. So if you have, well, here we have 3 geometries. Again, we take the metaphor of universe, which is in 2 dimensions, because it's difficult to draw that in 3 dimensions, of course. And omega is the density of the universe. So it's a dimensionless constant, and you divide by the critical density, which is 10 to the minus 29 gram per cubic centimeter, meaning that our universe is very, very dilute. It's 29 orders of magnitude less than, for instance, this table, which is of the order of a gram per cubic centimeter. And if you have more than this density, the universe will be finite with a positive curvature, like the surface of a sphere. If it is lower than that, then the universe is infinite, and the negative curvature is represented by this saddle here. And in the middle, you have a flat universe. And we know that we are in this configuration, that the universe is flat. So we are in this today, it's written here, that because of the lambda. I will come back to the lambda. In fact, that Einstein said it was not very beautiful. Why we have this information of a flat universe? I will try to give you an idea in a few words. In fact, when you have these fluctuations, that the Planck image of the sky here, you see that there are fluctuation positive in orange and negative in blue. And you can count the number of fluctuations you have as a function of size. So here in the top of this, I don't know if I can control this, yeah, it's moving a lot. Here you have angles. So here is 90 degrees and then 1 degree and then 0.2 degrees and very small angles. So as a function of angle, you count the number of fluctuation, positive fluctuation, and you see there is a big oscillation here at 1 degree, and then secondary oscillation. What are these oscillations? In fact, these oscillations are sound waves, acoustic waves, that are the structure of the universe at the point of recombination. That is 400,000 years after Big Bang. Why? Because the photons, the light, and the protons and electrons are in equilibrium. So there are waves propagating, and there's no collapse because there is a radiation pressure that maintains equilibrium. So all this is well known. It is sound propagating in a plasma. You know the velocity of sound in the plasma is the velocity of light over square root of 3. And you know how much has a sound run from the Big Bang to 400,000. Of course, you have a ruler. And this ruler is this in blue here. And it is 450,000 years. Okay, light years. And this ruler, we have the observer here, and we are looking at this. If it is 1 degree, it means that the photons are going in straight lines. It is exactly 1 degree what we see here. But if the universe has a negative curvature, like in this blue here, you will see a smaller angle, and it will go in this direction. If the universe is open, it will go at smaller angle in this direction. And you see that the error bars are very, very small. You see only points, and you don't see the error bars. So there's a very great precision. We know that the photons from the last scattering surface to us are going to in straight lines, so the universe is flat. This is geometrical, very simple, and nothing to say. You cannot contest that. In fact, we understood that all this fluctuation, all this sky with Planck is like a fingerprint of the universe. You know a lot of things here. You have all these points. I've not plotted a fit there. You know how big are the error bars. They are bigger here because of the fluctuation of 90 degrees. You have not a lot. You have 2 or 3. But then for 1 degree, that's why we compare this by the fingerprint. And from the fingerprint, you can deduce a lot of the characteristic of our universe. You can deduce omega, the density of the baryons, that is protons, neutrons, and so on. Why? Because the third acoustic here is depending on the rebound of the density of the baryons and the density of dark matter. And in the introduction, you know that we have a big problem now because there is a lot of dark matter, which is 6 times more than the ordinary matter. And all these are imprinted in this fingerprint. It's like a police statement here. We measure these fluctuations by Planck, and you have the fingerprint of the universe. Omega, lambda is not 0, and Einstein was right at the beginning, in fact. So let's go back, in fact, to who was the winner, in fact. There is De Sitter also in 1917. He said, well, the Einstein equations are very difficult to solve. It's tensor and so on. And Einstein have added a lambda. I will neglect the matter, saying there is no matter, no energy in the universe, only lambda. And of course, it's easy to solve. The result is that you have a universe which is expanding in exponential way, very exponential expansion. And Einstein was not very happy with that, saying, well, your universe explodes. Well, so what? He says, well, it explodes. And indeed, when looking back, he was right. In fact, what we are measuring today is an expansion of the universe which is accelerating like mad and which is exponential. So it is a De Sitter universe. De Sitter was right. Although it was a cartoon trying to laugh at De Sitter, but he was right. And of course there was other people, Lemaitre, Friedman, trying to solve this Einstein equation with matter and neglecting lambda, and they retrieve all these possibilities that I've already described, but still De Sitter was the alone to have the lambda inside. And then, of course, Einstein realized in 1931, when he saw that Hubble discovered the expansion of the universe, that you didn't need lambda. Lambda was there to find a solution, a static solution. And the universe is not static, so Einstein said, well, I was wrong, and he finally worked with De Sitter, and there was this Einstein-De Sitter model for all the 20th century. Nobody tried to introduce lambda again because Einstein said, well, it was an error. And it's not sure that Einstein has said that. In fact, when the historians have tried to see what was the truth, Mario Livio, for instance, recently he said, well, Einstein has recognized he was wrong, but he has never said it was its biggest blunder. In fact, it was George Gamow who said that instead of Einstein. And why? Gamow was a real actor in this universe knowledge. He wrote a paper in 1945 or something like that. And he was working with his student Ralph Alpher. And he published a paper the 1st of April already. And he has the idea of adding Hans Bethe, who did not do anything on the paper, but just to have alpha, beta, gamma paper. And so a great sense of humor, but in this paper it was a very profound paper, because he said that you need the Big Bang, because in the Big Bang you have a dense and hot universe where you have nuclear reactions able to form in a few minutes all the helium, deuterium and lithium, all the light elements that you see in stars now, they are formed in the Big Bang in the first minute. And that's true. When you look at the sun, you find a lot of helium in the surface, but this helium is done in the Big Bang, not in the sun. Although in the center of the sun you transform some hydrogen into helium, but it's negligible amount of helium that you have, especially since the helium will then move to carbon, azote and oxygen and so on. But in the universe you have 10% in number of helium, that means 25% in mass, because helium is more massive. 25% is coming from the Big Bang. So all helium that you see in stars and around you, and we have seen in the lab recently, cold helium, is coming from the Big Bang. And this George Gamow discovered in this paper, and this was confirming the Big Bang. If you had no Big Bang, you will not have all this helium in the stars. Now, we can come back on this cosmological constant. Why Einstein introduced that? It was to have a static universe. Okay. But then his universe was a sphere, well, a positive curvature. Remember that in our metaphor, it's only the surface of the universe that we are considering with a lot of galaxies. And the radius of the universe is inversionally proportional to lambda. There was, at this epoch, at the beginning of 20th century, it was also a big progress in quantum mechanics. And Wolfgang Pauli, who was a main actor of quantum mechanics, has the idea to say, well, there is lambda, which is equivalent to vacuum energy, because it is the second term of Einstein equation. You have the first term is geometry, and the rest is matter and energy. So if you put a lambda, it's a vacuum of energy, okay? Energy of vacuum. And he has the idea to say, well, we know in the laboratory that we have, when you have no particle at all, when you have only the vacuum, there is a fluctuation of energy due to the uncertainty principle. You have, for instance, delta E and delta T equal H bar. So you know that there is very small amount of time, delta T small, you have big delta E, and you have big fluctuation of energy. You cannot have zero as energy, you have fluctuation of energy. So you say, well, maybe this quantum mechanics energy of the vacuum is that of the universe. But if you make all the figures here, you end up with a universe of Einstein of 31 kilometers, which is ridiculous, meaning that finally it doesn't work. And we can say, well, maybe it was at the beginning of quantum mechanics. But now we have other theory of quantum mechanics. We have progressed a lot. We have now the quantum chromodynamics. You know that the protons is the elementary particle or quarks, and the protons and neutrons are formed by 3 quarks like this. And you have QCD and so on. So we have a much educated view of the vacuum. And still, if you extrapolate this vacuum to the universe, you find 100 times in magnitude, 10 to the 100, more energy than you measure in the universe. So our lambda, vacuum of energy in the universe, is very, very small. So it doesn't work. There is something wrong. And of course, we know that we never found, even Einstein tried to find, a theory that is merging quantum mechanics and gravity, and we are still searching for. And maybe it's come from that. When you extrapolate quantum mechanics to the universe, it doesn't work, but it doesn't work by hundreds of orders of magnitude. Now, we can just question, is this vacuum energy real? Yes, it is real. You have the Casimir effect, that if you have 2 plates, 2 metallic plates, and of course, in between the plates, you have the vacuum. And you see that the plates are attracted to each other. Why? Because in fact, you have a fluctuation, virtual particle, virtual photons in the vacuum. And then, since inside the 2 plates, you have a resonance, so you need only to have some of the photons, not all, because of this resonance, then you have less energy in the plates, and then they come towards them. So the vacuum, the energy of vacuum, is a reality in the lab. We have the proof of that for 30 years. People have measured 30 years this effect. Now, this lambda has a lot of story, because it was introduced in 1920, it was suppressed, and in 1998, it was rediscovered. Stars can be more massive, but then there is a factor 100 more mass than visible mass, which is huge. It's even much bigger than we know today, because this ratio is factor 6. But in fact, what Zwicky has not is that he has not the X-ray view of the universe, and we know now that in clusters of galaxies, all the mass, ordinary mass, is in very hot gas, 100 million degrees, and there is 10 times more mass in the hot gas than in galaxies. So that's why it was much more dark matter than we know today. But anyway, the hypothesis is that either there is a lot of dark matter, or even that Newton's law has to be changed. Because, in fact, this dark matter is manifested only by its gravity. So either you have the gravity change and no dark matter, or you have a lot of dark matter in gravity. That's already at this epoch. It was like that. Also in galaxies, and then you have Vera Rubin, who was a pioneer in this. And in 1978, of course, in 1970s, nobody was believing Zwicky, because Zwicky has ideas of genius in some parts, but in the others, he was wrong completely. For instance, he did not believe the Big Bang, while it was admitted at this epoch. And also, he was arrogant and taking all these, his collaborators by spherical bastards. And spherical because he was bastard on all the sides and all the point of views. So he was really a bad character, and it's only in the 70s that astronomers were convinced that dark matter exists, and it was from the rotation curve of galaxies. Here you have the velocity of rotation. Galaxies are disk, and all the matter is rotating around the center. And you can plot the velocities as a function of the distance to the center. It was difficult at the beginning because there was big error bars, but after a while, and especially with the gas, because the gas is going 4 times at higher radii until this here, and the gas was discovered by the 21 centimeter line of the hydrogen in the 50s, and then in the 70s there was a lot of galaxies mapped in hydrogen, and we discovered that there's a lot of dark matter. So all this was the history of dark matter. And then people tried to know what is this dark matter. And they make some simulations here with several possibilities. And the dark matter can be hot. Here you have a formation in the computer of the whole universe, and you find structures, filaments, and so on that you are observing. But here you see you have not the small-scale structure, and here you have the small-scale structure. So why? Because when it is hot, and hot means that the particles are relativistic when they are decoupling and forming the first structure. If it is relativistic, it's like the photons. You have a radiation pressure, and it prevents the matter to collapse, and then you have only the big scales. Okay? So already at this epoch, although we are discovering at this epoch that the neutrinos, which in the standard model have no mass, they have a mass, a very small mass. So they could be the dark matter, but in fact not, because they are very hot, and then they form structures that do not correspond to the observations. And then you have the cold dark matter, and this corresponds to observation. You have small scales, some galaxies and cluster of galaxies. And that's why from 1980s or so 50 years from now, all people believe that there was cold dark matter, and we call these candidates of dark matter WIMPs, that is, weakly interacting particles. Of course, they are weakly interacting, because if it was strongly interacting, we would have detected them for a long time. And these particles, which are not in the standard model of particles, they were in a supersymmetric, hypothetic supersymmetric particles, and the most stable was the neutralinos. And they should have 100 GeV in mass. That means 100 times the mass of the proton, which is around 1 GeV. So 100 mass of the proton. And the big thing is that in 2012, in CERN, when you put in the Large Hadron Collider, you put 2 protons colliding, and they are colliding at such a very high energy, then they are producing a lot of particles, because E equals mc squared. So in this collision, you are able to have particles created that are 100 times more than the proton mass. And this we discovered in 2012, the boson, Higgs boson, which is 125 times the mass of the protons. And although it is very, very short-lived, nanoseconds, we are able to discover it. But the dark matter particle, which is there for 13 billion years, we have not seen it. And the energy of the LHC has been increasing. We are not at 10 times more and even more, and there is no particle. There are no supersymmetric particles. So this is really not the good candidate. We have several other candidates of dark matter. Warm dark matter, which is that we are assuming a lot more far-fetched hypothesis, more speculative. That is, there is not only 3 neutrinos, but 6 neutrinos. We invent 3 other neutrinos, which are 1,000 times more massive than the neutrinos, and which could form warm dark matter, or self-interacting dark matter, or whatever. And now the most fashionable is fuzzy dark matter. And fuzzy dark matter means that you have a very, very, very small mass, 10 to minus 22 electron volts, so much more lighter than the neutrino itself. And these particles are quantum particles. That is, they have the manifestation of the fluctuations due to the Heisenberg uncertainty particle, but not only on the size of the Planck's size, that is at 10 to the minus 30 or centimeter, but on light years. And what we want to reproduce is the core of dark matter that you see in each galaxy, and which has 3,000 light years in size. So simulations have been done in this fuzzy dark matter. You see that there is a core in a galaxy, but you see a lot of fluctuation, and these fluctuations are quantum, so they cannot be damped. They are always there, and even if you interact two galaxies, there will be a lot of fluctuations. Even in the filaments in between galaxies, there are a lot of fluctuation in blue here, and this constrains the mass of the fuzzy dark matter. So it's not sure that it will remain a long time as a good candidate. Now, there is also another possibility, like even Zwicky said, that you can modify gravity. And in the 80s, in 1983, when it was realized that indeed the dark matter is not ordinary matter but exotic particles, then Milgram here, Moti Milgram in Israel, devised that maybe you can modify it, and in which way you can modify it. It is in weak fields of gravity. The weak field, that is the acceleration of gravity, or the force per unit mass, is g, the constant of gravitation, m over r square. So if this acceleration is large, over a certain amount, here it's the right part of the diagram, here the acceleration is put in abscissa, and here you have the ratio of the dynamical mass that you need to explain the rotation of galaxies and so on, and the visible mass. And you see that it is exactly 1 if you are in strong fields. In strong fields, you don't need to modify gravity. You need to modify gravity in weak fields. So the weaker the field is, the large discrepancy between the visible mass and the dynamical mass. So what does it mean? It means that, for instance, in the galaxy like the Milky Way, you need to change gravity only after the sun. In all the center, you don't have to. Only in the halo, and of course in the solar system it's perfectly normal Einstein or Newton gravity. So we have no experiment, only astronomers have experiment of these weak fields, and that's why they find dark matter after all. But you have also in the dwarf galaxies, even in the center you have a weak field, and you need dark matter in the center of dwarf galaxies, but not in big galaxies. So it works very well for all galaxies, but there are some problems with this mode. That's why people are, I just make the story short because I want to finish, but there is a lot of modified gravity. I will not tell all this Einstein ether, and the ether was eliminated in the 19th century, but it's coming back, you know. There is and then I want to speak about a tension that has recently arisen about the distance again. I spoke of distance at the beginning and the supernova for the acceleration, and again we have a problem with distances and the Hubble constant and the Hubble-Lemaitre constant. So here you have what we call a ladder because we have distance scale by different indicator of distance. You have the Tully-Fisher relation, you have the Cepheid, you have other variable stars and so on, supernovae, and then all this it's coherent ladder to give you all the distance of galaxies like this. But this is a direct measurement of the constant. But when you look at the cosmic microwave background, so very nearby the Big Bang, when you go to 400,000 years after the Big Bang, you have this last scattering surface here, and of course it's not a direct measurement of H0, but as I told you, it's a fingerprint of the universe, and according to the lambda CDM model, you can deduce H0, but it is indirect. So this value is 67, and now the direct value is 73, and there is almost 4 sigma. Sigma is a variance difference. So people begin to think that it is a big difference, a tension, and they are excited about that because this means that the lambda CDM model is not right. You have to modify it. So people try, and there is in the literature 100 papers looking at the modification, and you can, for instance, augment the number of neutrinos, and it solves a certain region, but then it makes other region worse, and so on. So nobody has reason succeeded to make a theory which works. So just to give you an idea that there's a lot, even if we know a lot from the 20th century, where they did not know about galaxies, then there is a lot in the future. If you want to work in astrophysics, there is a lot of work. Well, and my last point would be about what is at the beginning. Now it's more speculative that I will give you here, is what are the problems. We have a problem of horizon. So what is the horizon? I talk about the Copernican principle, that we are not at the center of the universe. But still, we are at the center of our horizon. We are here, and all around we have a sphere. That means that we are not able to look outside of this sphere. But it is true, we have nothing special, in fact. So it obeys the Copernic principle that there is no special observer. All observer has a horizon around it. And why? It's because when you want to look far, so you look at very distant galaxies, here's a distant galaxy, even more distant, then the time, the photons, the messenger, which is only going at velocity of light, which is small finally, at 300,000 kilometers per second, this galaxy, this messenger has taken 12 billion years to come towards us. So we are seeing this galaxy in its youth, when it was very small age. And then, after a while, we are going to a time when there was no galaxies. And here, in orange, is the Big Bang. And that's all. There's nothing after the Big Bang. It's the beginning of the universe. So maybe it's an apparent horizon, okay? We cannot see any galaxies outside of the horizon. But of course, in reality, there are galaxies there. But they will never send a photon towards us because it will take more than Hubble time to reach us. And even since the expansion is accelerating, the horizon is going to shrink and we're not going to have more galaxies as a function of time. So, okay, this is the horizon. Now, the problem of the horizon is that when you look at this last scattering surface that I've described here, which is 400,000 only years after the Big Bang. The horizon, the radius of the horizon is the velocity of light c multiplied by the age. It is the path that the light have run from the Big Bang to this time. So it's only 400,000 light years. It's very small. So here in this image, it is 1 degree. So you have 45,000 degrees in this map. So you have 45,000 horizon. And this horizon, of course, it's a region that are not causally linked because the light has no time to go from one side to the other. So why it is so homogeneous? I've told you that it is a constant, the CMB is constant, and the fluctuations are only 10 to the minus 5. So they are exactly the same temperature at 10 to the minus 5. Why? They have not been able to speak to each other to say, this is the temperature that you must be. So this is a big problem that it's called the horizon problem. And what is the solution is the inflation. Inflation, why? You see that you have here the horizon in red, and if you inflate this region of the universe in gray by a factor 10 to the 30 in only 10 to the minus 32 seconds, of course in 10 to the minus 32 seconds, the light has not moved, has no time to move. So the horizon is still the red circle. It is the same, okay? But then you see that all this region, which appears for us bigger than the horizon, they come from the same region of space. So that's why they are coherent in temperature. So with inflation, you solve the horizon problem. You solve also other problems like the flatness of universe, because if you have something which is not flat, if you inflate by 10 to the 30, of course, and you are just living on the frontier here, then you have the impression it is flat. So it solves the flatness. And also, in the bonus, it gives you the origin of the fluctuations. Because we think, we have seen that there are 10 to the minus 5 fluctuations, which are the initial condition of the universe, but we don't know what is the source of this fluctuation. We think now it is the energy fluctuation of the vacuum. So at the beginning, in the first 10 to the minus 30 seconds of the Big Bang, you have only the vacuum. You have no matter, nothing. The quantum vacuum. So, of course, there is fluctuation of energy. If you inflate this fluctuation by factor 10 to the 30, they are no longer microscopic, but they become macroscopic of 1 centimeter. And then this will precipitate in matter, and all this overdensity will become structure with gravity. We'll have some filaments, galaxies, clusters, and also stars and planets in these galaxies. But, there is a problem with inflation. And this was the theory of Guth and Linde in the 80s. And they realized very quickly that you cannot stop the inflation everywhere. You can stop in our universe. Of course, there's inflation and then it is stopped. We know after 10 to the minus 32 seconds, the stop of inflation and the precipitation of matter. But you cannot stop everywhere if the universe is infinite. So what you can imagine is that there are several universes. And sometimes the false vacuum here, which is expanding and expanding like mad, there are in-between universes here. You see at the beginning you have only the vacuum, and then one universe and then several universes. The universe will never communicate because in between universe you have a vacuum that expands by 10 to the minus 30 every 10 to the minus 30 seconds. So it's huge. You never have connection between universe, so you will not know. But at least you have the impression that there is multiverse. And this is, of course, speculation. I don't know if it is true, but it is the image that you have outside when you try, like a Flammarion people, to go outside the celestial sphere to know what it is. In fact, you have maybe a multiverse. Maybe, if the inflation is right, and it is an image from Andre Linde, one of the father of the inflation. And we are, where are we? We are in one of these bubbles, maybe let's say the red one here. We are a very, very tiny region. Our horizon is very tiny here, the point here, and we don't know where they are, the other universe. In 3 dimensions, you don't need a many dimension for that. This is an artist view of this multiverse. But you said, well, what there are alternative views. The inflation is the most theory that correspond most to observations. But there are some marginal alternative ones which are coming from the tentative to solve the quantum gravity by strings and the extension in membranes. So you have brain cosmology. You have some of these brains here. And some people have a large imagination and have imagined that you have 2 brains like this. And after 2 brains are colliding, they are very hot, and this is the Big Bang. And after a while, they are colliding, they are going away. Some galaxies are forming in the brain here. And after a while, by gravity, they come back, and they have another Big Bang, and so on and so on. But there are many, many problems with this kind of alternative theory, Big Bang bounce, and so on. You have a question of entropy, and it's even worse than inflation. So I will finish my history here. You have seen that how all this knowledge of the universe has become more and more solid with time. I've just finished with a lot of speculation about inflation, but for the moment, the inflation is favored by the Planck observation that correspond better to what we observed in the CMB. At some point, we could have found this primordial gravitational wave that is predicted by the inflation, because the inflation is so violent that it will make the universe resonate with waves, gravitational waves. And this is very strong gravitational waves that at some point we thought that we had observed in Planck, but it was only a foreground emission by dust, so it was not a real discovery. But at some point we are hoping to be able, by the next missions, to discover these primordial gravitational waves that will prove inflation, and we will progress. So thank you very much.
Thank you very much. I would like to express the gratitude of the University of Warsaw by presenting you this little token of our gratitude. I would like to say that we asked our florist for the flower arrangement to resemble the spectral characteristic of the universe. We asked that the buds are expanding into full-blown flowers and that the structure of the arrangement has both clusters and fibrous structures. So, thank you very much.
Thank you very much. Beautiful.
So we can wait for the technical staff to take care of the bouquet. And, oh, thank you. And I am sure that as with every lecture, it provoked lots of questions. So I would like to encourage you to ask questions to Professor Combes. And of course, the working language of our meeting is English. If someone of you would feel unsafe asking a question in English, please ask it in Polish and I can translate. So are there any questions?
Yes, sir.
Thank you for the lecture. I would ask about dark matter. Is it possible that it contains tachyons or any other particles that we haven't seen yet because of its unusual nature? Like I asked about tachyons.
Tachyons. You mean particles going faster than light?
Yes.
No, in fact, there are no tachyons. They don't exist. There was an experiment by the Opera mission near the CERN. In fact, they were courageous enough to say that their experiment think that some neutrinos were going faster than light, but it was not true. So it's impossible. There's no tachyons. It's a too speculative hypothesis, and it's impossible. With respect to Einstein and to any theory, it's impossible to go faster than light.
Are there further questions? Yes, please. Oh.
Well, I have a question. What is actually the difference between black hole and event horizon?
The black hole and the event horizon?
Yes.
Well, the black hole is something completely different than this horizon. The word is the same, but here is the horizon of the universe. And the black hole is a very compact mass, in fact. And it's so compact that the gravity is very strong. And there is an horizon, and the horizon is a radius below which you have an escape velocity which is larger than light. So nothing gets out of the horizon. Here it's a little different. It's a big horizon, billions of light years. The horizon for the sun would be 3 kilometers. Very small. And of course, inside the horizon, nobody has been able to see what it is, but everything is pushed toward the center. And then we have a problem of strong gravity to have a quantum gravity. And then we don't know exactly what is at the center, but at least all the mass will go to the center in horizon.
There is a question over there.
I want to ask if I understood it well. The inflation explains both why the universe is homogeneous and why there are structures in the universe, because it sort of stretches the space, and I don't understand the homogeneity. Seems to be the opposite of structures
yes.
being
it's a good
stretched.
Question, a good remark. Homogeneity was on the scale of the horizon, so big scales. And of course, you need to have a temperature constant at the last scattering surface. So, and it is homogeneous. With inflation or without, you have a homogeneous universe. You see that the universe is constant. There is a relic of radiation, which is exactly at 2.73 Kelvin. and the fluctuations are only 5 orders of magnitude below that. So it's perfectly homogeneous. There is no galaxy, no structure, and so on. It's later that the structure are coming. So the inflation inflate the small, very small, 10 to the minus 30 centimeter, small fluctuation of the quantum vacuum. So these are very small. And they, of course, if they remain small, they will be cancelling out, they will be damped and annihilated, and then you will see exactly no structure at all, no fluctuation at all. So if you want to use this fluctuation of the vacuum to create the fluctuations, you have to inflate by a factor 10 to the 30 in very small amount of time. So these fluctuations become centimeter-like. But then a centimeter with gravity, they will become kilometer and then a light year and so on and so on. Gravity will take up, then will take the relay, and then you will form the structure. But much later you form the structure. Here, when the universe is homogeneous, it's only 400,000 years after the Big Bang. The first structure comes 200 million years after, and until 1 billion years you have galaxies coming in. So you need 1 billion years to form galaxies. So it's much later. So inflation, you still have homogeneous universe at the last scattering surface. But the fluctuation has become 1 centimeter. Very small.
Any further questions? So if I can continue the previous question, you said that the tiny overdensities that caused the temperature fluctuations in the CMB are the same overdensities that caused the gravitational collapse and the growth of structures.
Yeah.
So does it just make a nice story, or do we have numbers to crunch to corroborate this?
Exactly, we have numbers, and we have a lot of people have reproduced the formation of the universe in computers. So, of course, we call this simulation Horizon simulation. In Paris, there was a group, Horizon simulation, and we have a cube of all the horizon, and we put fluctuation exactly what measured by Planck, because it's a real initial condition of the universe, and then we let gravity act, and we form galaxies and filaments and so on. The filaments are seen because the filaments are essentially dark matter, but you find galaxies like cake, the sugar and the cake here. The galaxies are tracing the filaments. And if you had not this initial condition, you will not find filaments, you will find something else. We have simulated in a simulation with other initial conditions, and it does not look like filaments and the cosmic web. So the cosmic web is there because you have the right initial condition that we measure in Planck. So exactly, we have numbers in the simulation, it works perfectly.
Okay, further questions? Anybody has the courage and interest at the same moment? Yep.
Thanks. Just so I understand, inflation is a good explanation for some facts, right, evidences, but do we have a good idea why it could have happened in the first place? What could cause actually the inflation?
It's a good question. We don't know, but it looks like a bit like lambda. You know, lambda is the energy of vacuum, and it is accelerating expansion. And you have, it's like the de Sitter constant that de Sitter put in the Einstein equation. If you put a lambda, you will have an exponential increasing. So it's, of course, it looks like, but it has not the same numbers, because the expansion of the universe is taking billions years, and here is 10 to the minus 32 seconds. So you have to put a much larger lambda, and it will be exponential for a while. So in fact, we need a scalar field, and people have simulated the dark energy now by a scalar field, the quintessence, the fifth element. So you invent as well for the dark energy now, but it's very moderate, the acceleration. The same for the inflation. So people put a scalar field, and it's all. It's simple, but we have to explain why there is a scalar field. But the scalar field is a fifth force. So we have to admit, when you have discovered the fourth force, you have the electromagnetic, the weak field, and so on, you don't explain why there is this force. Now you observe it, and you are obliged to admit that the force exists. And if it's the same here, we observe something, and you say, well, this is the manifestation of the fifth force. At some point, you have to admit that it exists, and you have not explanation why it exists. It's a metaphysical question, maybe.
Another question in the back.
Like you said, there are so many universes, and is who?
I've not understood the question.
Was there one big bang for all the universes, or every universe have their single
indeed,
big
you're
bang?
right. In fact, all the universe I've plotted here, they have different fingerprints. So it's a fluctuation, so it's random. And in one universe, you can have omega baryons, which is less than 5%. In your universe, 5%. You can have a dark matter, another ratio. You can have dark energy, another ratio. So all this is initial condition for universe. You can have some of these universe that are too dense and they recontract in a big crunch. Some will stay billions of years like our own. Some are very short-lived, some are long-lived, and so on. So it's only initial conditions given by the randomness of the fluctuation of the vacuum behind. So you can have all what you want.
Okay. Are there further questions? I seem not to see any. So, yeah, there is one. Thank you.
I have heard this debate that we need dark matter and modified Newtonian dynamics to explain the universe. Is it true that we need both of these things?
No, I think it's too much. It's too much.
Too much.
Because you have too much free parameters that either you have dark matter and normal gravity, or you modify gravity and you have no dark matter. But if you put everything, it's too easy. You will always find a solution because you add a free parameter as you want, and it's very easy to tune to that. The goal of the modified gravity is to get rid of dark matter and also of dark energy, because if you have a fifth force, you have some free parameter already in the equation of the Einstein equation modified by some factors, and then you can choose this factor to solve the dark matter and the dark energy in the same time. So you must be very cautious, but then the goal is there to have the fifth force, maybe a tensor and a vector force and a scalar field. But after this transformation, if all works well, you get rid of all the dark sector. That's the goal, but mixing both, it's a failure, because you want to get rid of this. And the big problem of the dark matter is it's like the epicycle of Ptolemy. It can fit. Ptolemy were fitting the orbits of planets. Okay, it was complex, but it was fitting. But we want simplicity, like Copernic simplicity. And we want that you have not all this. Dark matter is very easy. You put dark matter when you have a problem. You put some dark matter there and put dark matter there. It's too easy. Dark matter is enough. You have not to modify gravity. You explain the universe with dark matter. It's always the problem is that there is no particle, no supersymmetry, no particle. So this is a big problem that people tend to forget, that there is no dark matter particle.
So I think it's going to be the last chance of asking a question. Is there anyone who needs it now? I can't see any further questions, so I would like to thank Professor Combes once more. and to thank you all for coming and all our YouTube viewers for spending so much time with us. Thank you very much.